Okay. So now we will learn about YOLO, their improved version. So last class, we learned about the YOLO, right? So I hope you guys all understand the mechanism of the YOLO, right? And actually, I explained the version 1 of the YOLO, and I will explain version 2 and version 3 of YOLO in this class. But I mean, YOLO, their current latest version is like version A, right? So this expression could help you understand what was improved after the version 1, but for understanding the state-of-the-art YOLO algorithm, you have to maybe read papers by yourself or read some technical reports by yourself, okay? But one thing is, after version 3, YOLO was maintained by the author of YOLO version 1. But after that, YOLO version 4 to YOLO version 8, it was not maintained by the author, but by the other guys, okay? Anyway, the original author quit developing this YOLO detector because he think this algorithm could be used for some bad purpose, like killing persons, maybe. So he said in his technical report, maybe, yeah, he quit the job. Okay, anyway, after that, people improved this from other people. This YOLO was maintained. Okay. And this is the statistics of the YOLO, their performance. So this is the fast RCNN and this is the YOLO and their error analysis. So the slide has been slightly changed from previous lectures. So you have to re-download. Okay, I re-upload the revised version of the slide. Slightly, it was changed. So please re-download. Sorry about that. Okay. Anyways, the problem in YOLO was it records high error in localizing the bounding boxes. So it is rather good in classification score, but it was not very good at detecting bounding boxes. Okay, so the localization error is larger than the fast RCNN based algorithms. Okay, so yeah, but for other things, for background region, it is better than RCNN based algorithms, but for the bounding box regression itself, their performance was quite limited. And another problem was their recall was low. Okay, so maybe some of you are not familiar with recall, so I made this slide. So recall and precision, this is quite important concept. So I made another slide to explain about this. So this recall and precision, those two are frequently used measure for evaluating the performance of the system, okay, machine learning system. So recall is meaning the coverage of the ground truth. Okay, so how many portions of the ground truth your system will recover? That is the recall. And also the precision, it means the correctness of your estimations. Okay, so among all the estimations outputted from the system, how many portions are correct? Okay, that's the precision. And recall is slightly different from the precision, and it says how much the estimations are covering the ground truth. So I usually explain the recall and precision using this kind of figures. So let's instead of the machines, instead of the systems, let's assume we are measuring some person's performance, right? So if she speaks much, then there is the probability that she says ground truth. Okay, she says something similar to ground truth. She sometimes say some fact which is far from the ground truth. Okay, so one can say anything, right? Some are close to ground truth, but some are far from the ground truth. Okay, but recall means because she speaks a lot, among the things she speaks, ground truths are already covered. Ground truths could be already covered, right? If she speaks a lot, then even though she speaks some fault things, something wrong, but she can cover most of the ground truths. Okay, but then in that situation, we can say because she covered most of the, if she covered most of the ground truths by saying a lot, we can say she has high recall. Okay, but based on the precision, maybe she may have less precision because she say a lot. Among the things she said, there could be a lot of fault things, right? So precision is measured by dividing the number of correct things by the total things she said, right? So let's say she said half fault things, half incorrect things, and half correct things, then her precision could be 50%. Okay, but by saying a lot, let's say she said already all of the ground truths, then her recall is 100%. Okay, are you guys understanding this? Right? And when the system or the human is not saying much, let's say one person, he say only 2 words in his entire life. Okay, then he may not cover all the ground truths in the world, right? Because he say only 2 words. That 2 words was correct, right? But that 2 words was too to say small to cover all the ground truths in the world, right? But we can say if he say 2 ground truths, then his precision is 100%, right? But his recall could be very small. Okay, right? Are you guys understanding this? No? Maybe all know this, right? 다 알아듣고 있나요? 그러니까 하이리콜은 그러니까 말을 많이 하면은 막 틀린 말도 하고 맞는 말도 하잖아요. 그러면은 반반 말했다고 하면은 프리시전은 50%밖에 안 되겠죠. 근데 많이 말을 하다 보니까 얻어 걸려서 진실을 말하게 되면은 뭐 세상에 있는 모든 진실을 다 말하면은 이제 100%가 리콜이 될 수도 있는 거잖아요. 그렇죠? 그리고 말을 많이 안 하는 사람이 있고 이 세상에서 태어나서 지금까지 2단어밖에 말 안 한 사람이 있다면 그 사람이 2단어를 추루를 말했으면 프리시전은 100%인 거죠. 근데 2단어만 말했으니까 세상에 있는 진실을 다 말하기에는 커버하기에는 힘든 거죠. 그러니까 리콜은 되게 낮겠죠. 네, 그 얘기를 하는 겁니다. 그래서 so for normal system, there's some trade-off between recall and precision. Okay? So we have to always measure both measurements for one system. Okay. So to increase the precision, one system can reduce their output. Okay, so I mean, given learned parameters, he can hide their real performance by reducing their output. Okay, so to fairly measure their performance, we have to measure two things. Okay, but the thing is, YOLO, their recall is quite small. Okay, quite low, right? So in that sense, YOLO is estimating less bounding boxes compared to the fast RCNN, and also their localization error is also low. Okay, so their estimation, bounding box estimation, is also not very correct. Okay, that was the problem in YOLO. So the next paper, the original YOLO paper was published in CVPR 16, and after 1 year, the same was published YOLO version 2 in CVPR 17. And as you already seen, RCNN streams are here. Okay, so x-axis they are denoting the speed, okay, and the y-axis they are denoting the accuracy. So as the RCNN and fast RCNN and fast RCNN, they are improving the speed and also the accuracy. And YOLO version 1 was here. They are so fast, but their accuracy was less than the accuracy of RCNN. But YOLO version 2, they improved some localization error, and also they added some other tricks, other heuristics to improve the YOLO version 1. And as the result, the performance is sometimes there are actually also give some variance by varying some hyperparameters of YOLO version 2, we can obtain different speed and different precision. Okay. Actually, there are 5 versions in YOLO version 2, but in some of the version, you surpass the fast RCNN accuracy, and also it's faster than fast RCNN algorithm. Also, it's real time. Okay, so this is YOLO version 2, and this is this slide is showing that which components was added in YOLO to improve it. So there are a variety of things to be improved. So yeah, I will explain you about these items in the subsequent slides. Okay, so maybe you already know the in this period, in 2016 and 2017, the batch normalization was proposed. Okay, so this is solving this invariant, this covariant shift phenomenon. Okay, so let's say this is the neural network you are making, you are training. Then this is some layer, right? This is another layers. Then if you visualize the outputs in different layers, then their distributions are quite different. Their scale, especially for the scale. Okay, so let's say in this part, if you visualize their actual values, then actual values could be around 100, maybe 100 to 200 in some layer. But after some layer, the output could be bounded to maybe 1 to 2 value, or in other layers, the ranges of the values in this output could be like very big, like this. Okay. So especially for the scales, there's no constraint in the neural network, right? So we in previous neural network training, there was no schemes to bound or to give some constraint in the scales of these responses. Okay. And actually, the author of this batch normalization layer, they proposed, they figured it out that this scale can kind of spoil the training. And this may make the convergence of the training slow. So what this batch normalization algorithm they do is they do normalization for each layer's response. Okay, so they all make their output distributions towards the standard normal distribution. So they now they will have all zero mean and also the standard deviation of 1. Okay. They are assuming this, and if their scales are, the uniform, following some standard deviation, or if their output in the intermediate layers of the neural network, if they follow the same distribution, the normal Gaussian distribution, then they assumed that the network will converge faster. And indeed, by experiments, they validate that. Okay. So this is the simple algorithm. So the thing you have to do is during the training, you are processing multiple images, multiple samples, and we call it as batch, right? For example, the batch size is normally like 10 to maybe 50, maybe, yeah, it depends on the implementation, but normally we use multiple images at once for training, right? We use 10 to 50 images at once when processing the training. And for that 10 to 50 images, we find the mean and variance of that, okay? And then we normalize to make their distribution to the standard Gaussian distribution, okay? And then after processing, you can unnormalize it, okay? You can unnormalize it to regenerate the original signal, okay? So this is the batch normalization, and this could be happened in training without any. So in the training, this mu and sigma could be calculated from seeing the batch, right? But thing is, in the testing, there could be just one sample inputted, okay? During the training, we have batch, right? But for the testing, normally we use batch size as 1, right? So during the testing, sometimes we cannot recover the mean and the sigma values, right? So because these values are depending on the samples actually used, so we cannot kind of recover this mu and sigma if there is just one sample in the testing. So during the testing, we actually infer these values, okay? Actually, that are inferred from some layer, okay? Mu and sigma. That's the batch normalization. So, okay. And so if you use the batch normalization, this is the training graph based on the epochs, right? And it suffers to converge if you do not use any batch normalization. But with batch normalization, the training goes stable, okay? So this normalization, the scale, ignoring the scale of the responses in the intermediate layers, that is helpful for more stable neural network training. Okay. So in this YOLO paper, they involve this batch normalization and slightly improve their performance. Okay. Also, this is also very heuristic things. The original YOLO version 1, they used pre-trained network, the VGG16 network as their backbone. But these VGG networks, they are pre-trained by this size, this dimensional images sense input. But one thing is in YOLO version 1, they are using this sized image as input. So there's some gap between the input used for the pre-trained network and the input used for YOLO version 1, right? Even though they borrowed their backbones, but their backbone was trained for different resolutional images, right? So the author point out that, and also they fine-tune the VGG network to these resolutional images for like 10 epochs, okay? So after pre-training VGG on this sized image, then they fine-tune the network for these same dimensional images after that training, okay? And they also say it gives better performance, right? So these simple heuristics could give better performance. And also, this is the thing mentioned here. So VGG16, that's trained in 2 to 4 by 2 to 4 images, but they are fine-tuned on these 448 by 448 images after the original training. And also, this convolutional is meaning that they have FC layers at the last layers of the YOLO architecture before, but they remove these FC layers and instead use the convolutional layer. So FC layer and convolutional layer, they are almost the same, right? FC layer, but FC layers are inputting the 1D signal, but the convolutional layers are inputting the 2D signals, okay? But FC layers are almost the same as 1-by-1 convolution. So anyways, they also eliminate the pooling layer in the last layer and use the convolution layer, okay, to retain the high resolution images, okay? That's also heuristical things, but anyway, it improves the performance. But here, the performance was becoming less, but I mean, in this part, they are saying that their recall was improved, okay? When using the convolution, their MAP could be less, but their recall is improved. And also by changing these FC layers to the convolutional layers, they also can use some anchor boxes, okay? I will explain what anchor box is here. So previously, when you learn the YOLO version 1, I said the authors are divided by 7-by-7 grid, and for each grid, we estimate 2 bounding boxes, okay? That's what I mentioned before, right? So for overall images, we can estimate 98 bounding boxes, right? So we will divide whole images into 7-by-7 grids. So there are 49 grids in the image. And for each grid, we will estimate 2 bounding boxes. Then the overall bounding box number would be 98, okay? This is the YOLO algorithm. So you can maybe change it, the number of grids, right? But still the number of bounding boxes are limited, okay? This is actually the main reason why the recall of the YOLO is limited. So these anchor boxes, their concept was originally proposed in faster RCNN. Okay. So rather than, but when I explain faster RCNN, I omit this part because it's really bit complex. But the concept is quite simple. So rather than estimate the bounding box coordinate itself, you have some template like this, templates for the bounding boxes like this. So you have bounding boxes having different ratios like this. This is some manually defined bounding box template, okay? And for each region, you will estimate number of anchor box. You will estimate the boxes whose number is same as the number of anchor boxes. But how to use this anchor box is, anchor box have some initial width and height, okay? But their center position is here. The center position is always the center of the grid, but their ratio, their width and height are somehow initialized. They have some initial width and height. And the thing we estimate is the delta W, delta H, delta X, delta Y. So for the initial bounding box obtained from the anchor boxes, we will estimate their residuals. And it is known that estimating these residuals instead of directly estimating the bounding box locations itself is robust for training, okay? So in fast RCNN, they attempt these things. They have some template for the initial bounding box and estimate their residuals only, okay? And this YOLO also do the similar things. And later you will see some graph, and they use these 5 anchor boxes in YOLO version 2. Instead of the 2 boxes, 2 candidate boxes for each grid, they estimate 5 boxes for each grid. And also, because they remove pooling layers at the last layer, the grid size is increased to 13 by 13 rather than 7 by 7. Okay. So and also they slightly adjust the input size again. So previous YOLO, they used 448 by 448 dimensional input image as the this size image as the input to the YOLO. But in YOLO version 2, they use this 416 by 416 dimensional images. Okay, because during the deep learning process in YOLO version 2, they downsample the images by 32 times. So it will generate this dimensional feature, this 416 by 416, it will generate the 13 by 13 feature map at the last layer. And for this feature map, they generate 5 bounding boxes for each. And the resultant bounding box number would be 845 bounding boxes. Okay, this is much bigger size, right? Number of bounding boxes are much bigger in YOLO version 2 compared to the YOLO version 1, right? Because of this, the local, the recall could be improved. Okay. and yeah, this paper has much heuristics, but the reason why they changed this input size from 448 to 416 is they want some odd number for feature dimension. Okay, so normally a big object, they could be located in the center of the images, right? So their feature map, if their feature map have even number, then the center will have the center position of the feature map would not assign with the center bounding box. Okay, so they prefer, let's say this is 14 by 14. Then, if you think the center position, then that position will not be assigned to any feature map. So they won't have the odd numbered width and height for feature map to assign the center position bounding box. But this is also heuristic, right? Anyway, they do this. Okay. And anyway, by increasing the number of bounding boxes, this anchor box, that could improve the performance. But if you see this graph, you can see their MAP is not that increased, right? Sometimes it is reduced. Their MAP sometimes reduced. But what they insist is they can raise the recall from 81% to 88%. Okay. So anyway, they could reduce the precision of the model, but reversely, they could improve the recall, right? So anchor box, that is related to this. And this is something about the anchor box initialization. So I mentioned that previously the anchor boxes are manually initialized. Okay. So normally we use some bounding box whose ratio is 2 versus 1 for width and height, or 1 versus 2, or 1 versus 1. We use this type of ratio by manually defining it. Okay. But in here, dimension priors, what they mean is they apply the k-means clustering on the bounding boxes in the training data and make some initial anchor boxes from the data statistics. And also they measure how many anchor boxes are kind of optimal, and they decided as 5 because it have good trade-off between recall and precision. Okay. So that's about dimension priors, and by involving dimension priors, also some MAPs are improved. Okay. And previously we mentioned that 5 values are estimated for one bounding box, right? But previously we somehow directly estimate the value of width, height, and center point and center point of the bounding boxes, the XY coordinate, and also the confidence value. But here, because we are using now the anchor boxes, we somehow use the information of the anchor boxes. So this PW and PH, they are initial anchor box size. Okay, these dotted lines, they are indicating the original anchor box size. But we estimate TW and TH and apply some exponential function on that. And somehow we are shrinking this we are anyway estimate some ratio for this original initial anchor box size now. So previously we directly estimate width and height, right? But now we estimate the ratio of relative to the anchor box size, okay? And also we somehow bound the X and Y positions as well. So, and this is the anchor box center point, and we estimate the residuals to the anchor boxes now, okay? And so slightly, their values are same as before, but the encoding method was slightly changed, and this also gives some increasement in the performance. And there are also a few more heuristics. In original YOLO, they used this dimensional input, but because to make their feature map size into this, they use different sized input image, and also to involve multi-scaled, multi-resolutional images. They train by resizing the training images. So the resolution they used is this. So they are all times of this 32. Okay, because they think this 32 have some meaning because they are reducing the input size by, so their YOLO architecture is tend to resizing the input size by 32 times. Okay, they tend to reduce the input image size by 32 times. So they constitute the image resolution as the multiples of 32. Okay, and actually they use resizing scheme at every 10 batches. Okay, they train the network by resizing the input size to this randomly. Okay, so this is the multi-scale training, right? This is not very hard to implement, but this also gives us some improvement in MAP, right? And pass through a new network. They also propose some new network whose name is Darknet 19. So the YOLO authors is insisting that the VGG network, it is not very efficient for the object detection task. Okay, so they use, similarly to the VGG network, use 3x3 filter corners and double the channel after pulling step. So when we apply pulling, the image size are reduced, right? But instead they enlarge the channel numbers. Okay, so for example, the initial input would be like this. And first we maybe make it as 64, having some this kind of channel, right? After applying pulling, the image size could be reduced, but we then instead enlarge the number of channels like this, right? So actually they do similar thing. So this is what VGG is doing, and in Darknet 19, they do similar things. So when they reduce the input resolution, they double the channel number. Okay, so that's actually happened inside here. And also they involve the batch normalization to stabilizing the training. Okay, that's the Darknet 19. It's kind of similar, having the similar architecture to VGG, but have a few more modules. Okay, so they are insisting that this is a little bit faster than VGG. Okay. And okay, this is the result of the multi-scale training I explained here. So the performance is better. And another idea they use is pass-through layer. Okay, so that happened in here. Okay, their final output feature is this, which is the we have 13 by 13 feature map at the end of the network, but in the middle of the network, they have slightly bigger resolutional feature, right? But this would be bigger in channel, right? So they divided, this is the layer, the response obtained in the previous layers. They actually divide this into 13 by 13 dimensional vector, not vector, some array. And they actually flatten it like this. So they, this is 13 by 13. They divide it and concatenate it as a sequence. So this part goes here, and this part goes here, and another part goes here. So anyway, they concatenate this like this. Yeah, not this way. This part have to be here. This part have to be here. This part have to be here, here. Anyway, this wider dimensional 2D arrays, we divide their 2D dimensions and fit to make it same dimensional as this 13 by 13 signal, and concatenate it, and also concatenate this to the signals in the later layer. Okay, and then use this as the new feature to map the bounding boxes and classification score. So that is the idea of pass-through layer. So their motivation is use the higher resolution features with the low resolution features, and this helps to improve the MAP. Okay, so that is actually in somewhere here, right? So involving pass-through layer, MAP is for the improved. Okay, so anyway, the original YOLO, their MAP was 63, but YOLO version 2, using this kind of heuristics, they have better MAP. Okay, so by doing this, they can obtain the algorithm which have the real-time speed and at the same time robust accuracy. Okay, and this variant, you can obtain this by resizing the input image. Okay, so if you resize the input image in the low resolution image, then the speed could be faster, but the accuracy could be less. But if you make it in the high resolution, then speed could be less, but the accuracy could be better. So there are some trade-off between input resolution and the performance of the architecture. Okay. Anyway, these are heuristics used for improving the YOLO. Okay, and YOLO 3, this is not published. Okay, in the top conferences, but they published this in the technical report, the archive. Okay, and they say this further improve the performance. Okay, so actually the high level idea is they are using 3 different scales when estimating the bounding boxes. Okay, so this is kind of similar to the feature pyramid. In DTR, we used multiple resolutional features, right? We first extract this type of multiple features and then encode it with the encoder, decoder of the transformer. So this kind of features with different scales that are helpful for improving the performance. So this YOLO version 3 is also using that. So previously, for this number of grid, they estimate this number of vector. So now this 80 is the class number. So previously this was 20, but slightly changed it. And also they estimate some bounding box information, right? But another they estimate this number of scales, okay? So now they have 3 times more bounding boxes compared to previous, okay? So by involving this multi-scales, so I mean, they estimate bounding boxes, they have different resolutional features like this, and they estimate bounding boxes for each resolution. So this is the multi-scale schemes, and it improves the performance. And also they introduced the darknet 53, which have the deeper layers compared to the darknet 19 they used for YOLO version 2. Okay, and what they propose is similarly to ResNet, they have the residual connections in here, residual connections. They make it deeper, right? I already said in ResNet, they have the residual connection to prevent the vanishing gradient effect. So similarly in darknet, if they make it deeper, there occurs the vanishing gradient effect. So they prevent it using the residual layers. Okay, so they propose this darknet by saying that it is more efficient than ResNet to achieve the detection. Okay. Okay, this is the YOLO version 2 and 3. Okay, you can see a lot of heuristics inside, but anyway, the performance was improved. Okay, and also from YOLO version 4 to YOLO version 8, it also have a lot of heuristics, but the performance was improved. Okay, so it's worth to maybe study by yourself, maybe. And the other topics I have to maybe explain is this RT-DTR. This is the real-time pipeline proposed by the, based on the DTR, okay? So usually the transformer-based architectures are taking a lot of computational resource, but this RT-DTR, they are insisting that their DTR-based object detection pipeline is operating in the real-time manner, okay? So this is not also published yet. They are in the tech archive. They are just the technical report yet, okay? So they are comparing their speed, their latency, and their accuracy here. And they are comparing their algorithm with some real-time algorithms, YOLO version 5 to YOLO version 8, right? And they say they obtained the better speed and better accuracy, okay? So red point, they are RT-DTR performance. Their motivation is like this. In DTR, we use the multi-scale features, right? So from the image, we first extract this kind of multi-resolutional feature, and then encode this in the encoder-decoder of the transformer, right? But this is definitely helpful for improving the performance, but it hinders at the same time real-time speed, okay? So they are saying that they somehow optimize this part, okay? If encoder, previously we input all the resolutional features to the encoder as the input, but in some paper, it is analyzed that encoder accounts for 49% of the overall DTR operation, but they contribute only 11% of the AP, the accuracy, Okay. So it means we don't have to use all the multidimensional information in the encoder maybe, right? So this paper, what they do in the encoder is they do not have explicit, they have encoder here, actually, the encoder here, but from the multi-resolutional feature, they only use the higher resolutional feature here. Higher resolutional feature as the input to the encoder, right? And they use the remaining information as the input to some feature fusion module, right? So they encode the higher dimensional features as the feature via transformer encoder, but use the other resolutional information to fuse it later in the when we already obtained the encoded feature from the encoder. Okay, so this CCFM is based on the CNN. Okay, MLP layers. Okay, so by doing this, they can reduce the time complexity, the resources used for calculating the encoder. Okay, and then they could reduce the overall complexity of the DTR. Okay. And another thing is this IOU aware query selection is used. So I mean, previously in DTR, we also have the query selection method, but the difference is IOU aware. So not if we not use this IOU aware query selection, both classification score and the IOU score is important when choosing the query. Okay, but there are many queries that estimate high classification score but have low IOU scores. Okay, so it means among the predictions of the transformers, they are actually estimating the bounding box location, right, width, height, and center location, and also their class, right? The classification score meant here is class they estimate. The IOU score they mean is the bounding box information. Okay? They are saying that when analyzing the outputs of the transformer, the DETR, they observe that class score is good, but the bounding box location is rather bad in many query results. Okay, so they select the queries which have high classification score and high IOU scores. Okay, so that's the IOU aware query selection part. So the queries are reduced and the performance, I mean, the complexity in attention is reduced, okay? So this is two modules which were proposed by RTDTR, and their performance is quite impressive, better than the DINO, which is the state-of-the-art DTR algorithm, and also better than other deformable DTRs, their variant. Okay, so okay, I think this also you have the source code of this RTDTR in the GitHub. So I think this is worth using, maybe for our project or other real-world application. Okay. So this is the YOLO streamed algorithm, and this is the DTR streamed algorithm, and this is the RTDTR, their variant performance. Okay. So this is the end of today's lecture. Okay. Have any questions? Okay, if not, let's finish here. Thank you for attending.